Alright, so in this video I'm going to go over the answers to Friday's assignment as well as yesterday, what I gave you for the review. In yesterday's video I went over numbers 1 and 5, so I'm just going to pick back up with number 16. So in this one we're looking at a spread of a disease, quite appropriate for what's unfortunately going on now. Assume that the relative rate of spread of a certain disease is constant. Suppose also that in the course of any given year the number of cases of the disease is reduced by 20%, which means 80% is left. If there are 10,000 cases today, how many years will it take to reduce the number to 1,000? So we will, in a way, we're not going to use a differential equation here like what we were using in the past. We can actually just kind of come up with something based off of a little pattern here. So we're looking at today as the initial time. T equals 0 means that there's 10,000 cases present. And for each year after, it is decreasing by 20%, which means 80% is left. So if we took 10,000, we would multiply it by 0.8. The year after that, this amount up here, the 10,000 times a 0.8, will get multiplied by another 0.8. So each year after, we're just going to take the previous amount and multiply it by 0.8. So we could say the amount in however many years is going to be 10,000 times 0.8 to the t. So looking at this a little differently now, we want to know when it will decrease or be reduced to 1,000. So we're going to say 1,000 equals 10,000 times 0.8 to the t. Dividing 1,000 by 10,000, we're going to get a 0.1 is equal to 0.8 to the t. Take the natural log of each side. So the natural log of 0.1 is going to equal t times the natural log of 0.8. So t is equal to the natural log of 0.1 divided by the natural log of 0.8, which is approximately 10.319 years. Right, for part B, how long will it take to eradicate the disease, that is, to reduce the number of cases to less than 1? What we could do is just pick a number that is less than 1. So let's say 0.4. So if we were to set 0.4 equal to 10,000 times 0.8 to the t, I would divide 0.4 by 10,000. And then take the natural log of each side. Alright, so t is going to equal the natural log of 0.4 divided by 10,000 over the natural log of 0.8, and this gives us approximately 45.382 years. Now if we go back, like I said, I just picked a number, so we know it should be less than this because that's just to get it to 0.4. But let's say we did just set it equal to 1. So if I set 1 equal to 10,000 times 0.8 to the t, and I solve this the same way I just did, I would get t is approximately 41.275 years. So I could have just gone straight to that, and the answer to part B is going to be, it has to be greater than 41.275 years. But we also picked an arbitrary number just to know it shouldn't be any more than this, but it can't be any less than this. Alright, so looking at 21, we're given a differential equation working with money that's compounded continuously. So for part A, we're asked to solve the initial value problem for x as a function of t. So we start off here with dx over dt equal to 1,000 plus 0.10x. I'm actually going to kind of, in a way, do the separation of variables. So we could say that dx over the 1,000 plus 0.10x is going to equal dt, and then we'll take the integral of each side. I'm just going to write this as 1 over 1,000 plus 0.10x dx. Remember, anytime you take the integral, make sure you put that dx there, and then the integral of dt. Because we want to solve the initial value problem for x as a function of t. So I'm going to let u equal to 1,000 plus 0.10x. Then du over dx is just going to equal 0.10. And dx is going to equal du over 0.10. So continuing this over here, now we're going to end up with the integral of 1 over u times du over, I'm going to write it this way, 1/10 is going to equal t, we'll just write it this way, still the integral of dt. So over here I'm actually going to get 10 times the integral of 1 over u du equals the integral of dt. So then this becomes 10 times the natural log of u. Now we're dealing with money, so everything's going to be positive here. So we'll just keep this, put our constant, and then it's going to equal t plus our second constant. So 10 times the natural log, we could bring back in what u is equaling here, and this is 1,000 plus 0.10x. We'll just say plus c, all of this will equal t. Alright, so we want to solve for x now. So actually I could bring that back to the other side. So we could say the natural log of 1,000, get 1,000 here, plus 0.10x is going to equal t over 10 plus c. Again, I could just move that c over to either side right now. It doesn't matter if it's positive or negative. So at this point, I'm going to take a base of e, so we're going to have e to the natural log of 1,000 plus 0.10x is going to equal e to the t over 10 plus c. So then we just get 1,000 plus 0.10x is going to equal, separating this, e to the t over 10 times e to the c, and we'll just call that a. So now we'll get 1,000 plus 0.10x is going to equal a times e to the t over 10. And then x is just going to equal a times e to the t over 10. Subtract 1,000. And then that's a 1/10, so we really just multiply it by 10. Just kind of put this over here. So then x is going to equal 10a times e to the t over 10 minus 10,000. Alright, so that is our general solution. To find a specific problem, again, we're looking at our initial condition. So t equals 0 means x is 1,000. So if we substitute that in, let me continue down here. I'm just going to show our initial condition is that when t equals 0, x is 1,000. Alright, so we have 10 times a, e, again it's t over 10, so it's 0 over 10 minus 10,000. That's going to equal 1,000. Putting in the x is 1,000. So 10 times a, e to the 0 over 10, that's just going to give us 10a. And then we'll get 11,000 on the other side, so a is equal to 1,100. So therefore, x of t is going to equal 10 times 1,100. I'm just substituting into this equation right here. E to the t over 10 minus 10,000. Or you could just say it's 11,000 e to the t over 10 minus 10,000. All right, so that's the final answer for part A. All right, looking at part B. About how many years will it take for the amount in your account to reach 100,000? And this is just more straightforward. We're just using the equation that we just found for part A. So again, now this is saying A is 100,000. And then T would be what? So we're going to take this 100,000, set it equal, so I'm using this right over here. We're going to set it equal to 11,000 e to the t over 10 minus 10,000. So we're going to get 110,000, adding that to each side, equals 11,000 e to the t over 10. Divide both sides by 11,000, so this will actually give us 10 equals e to the t over 10. Take the natural log of each side. We just get the natural log of 10 is equal to t over 10. So t is going to equal 10 times the natural log of 10, which is approximately 23.026 years. So please make sure you go back over these problems, whether you're just watching this video once or twice, or you're retrying them as well. You really need to understand each step, showing each step with these. Alright, so looking at number 13, like I said, this was a bit of a challenge. We're going to start with some u substitution here. So right away, we're going to let u equal the natural log of y. Mainly because when we go to take this derivative, we're just going to get a 1 over y, and that's what's going to help us get rid of that y that's in the denominator. So then du over dy is going to equal 1 over y, and then y times du is going to equal dy. So now when I go to substitute this, we're just going to get the integral of tangent u over y times y du. So now this y and this y can divide out, and now we're left with the integral of tangent u du. Well, we run into another problem because we don't know the antiderivative of tangent u. Using another substitution is not going to help as far as like a u substitution. We can use a trig identity though, and we could rewrite this as sine u over cosine u. So I'm wondering if anyone gave this a try, and we'll leave it at du. Now we want to use another substitution. I'm not going to call it u substitution because we already used u up here. So we go to around the same letters of the alphabet. We're going to use w. So at this point, we're going to let w equal, and you just got to give it a try. What do we want to try to get rid of? I'm actually going to let w equal cosine u because it all depends on where the new part's going to show up. So if we wanted to try to cross off the sine u, this is what I'm going to use. If you tried it the other way, it would turn out that it just didn't work, and then you would go back to this step again. So then we would have dw over du is going to equal sine u, and now du is going to equal dw, actually it's a negative, dw over negative sine u. And then this is what's going to help us cross out that sine u that's up here. So now I'm just going to change colors here to show that we're changing this. So then we get the integral of sine u over w times dw over negative sine u. So the sine u's cross out. We're left with a negative integral 1 over w times dw. Alright, looking at this part, we're going to get the opposite of the natural log, the absolute value of w right now, and then plus c. But then resubstituting in what w is, that's that cosine u, so now we get the opposite of the natural log, absolute value of cosine u plus c. But next we need to substitute back in what u is, so now we get the opposite of the natural log of cosine. Remember, u is equal to the natural log of y, and then plus c. So if you were able to come up with that, great job. Some of these do require a little trades or substitutions, and if a u substitution isn't going to work, we have to try some sort of other substitution. All right, what I assigned yesterday was a quick review 1 through 8. So for this, I have everything already written out. I just want to talk about it. You definitely want to just start by just graphing f of x on your calculator. So this is the graph off to the right here of what we're getting. And we want to answer a few questions here. So it says find where f is continuous. Well, if we don't even look at the graph, we just go back to the function here. We know that if it's a fraction, our denominator can't be 0. So if our denominator is 0, we would say it's discontinuous then. So we set it equal to 0. But if you notice, it simplifies to e to this power. Even though it's a negative power, e to any power will never be negative here. So therefore, that denominator is never going to equal 0. So then we say, therefore, f of x is continuous everywhere. And we can verify that by looking at the graph. And just letting you know, like the window that I set here was from negative 50 to 50, counting by tens on the x-axis, and negative 10 to 60, counting by tens on the y-axis. And then I sketched my graph from that. All right, as you go through to find the first derivative and second derivative, you could use your calculator and define each function, so it's just a little bit easier to navigate through. But for 2, you could also just trace, keep increasing the values of x. So the limit of f of x as x keeps increasing without bound seems to approach that horizontal line of y equals 50. And then if we keep choosing large negative numbers here, it looks like our horizontal or the limit here is going to 0. But these are connected. Remember, limits at infinity are horizontal asymptotes. So that's what I have written here. So the 2 horizontal lines we're getting as we keep increasing and decreasing without bound is at y equals 0 and y equals 50. Now, as you were finding the derivatives of each one on your calculator, again, it looks very similar to what we were already given as our function. So the domains of each of those, the first and second derivatives, are also all real numbers. The denominator of each will be some power of this 1 plus 5e to the negative 0.1 x, which is never equal to 0. Therefore, they are defined everywhere, so their domains are also real numbers, all real numbers. And then we have the graphs of them. So for 5, it was saying draw a graph of f and find its zeros. Well, based on the fact that we have a horizontal asymptote at y equals 0 and y equals 50, f of x will never cross the x-axis, therefore it has no zeros. If you look at 6, looking at this graph also takes us back to 4 with the domain is still all real numbers. For 6, it's saying draw the graph of f prime and find the intervals on which f is increasing and decreasing. So here, our first derivative is always positive. Therefore, f is increasing everywhere. F is never decreasing again since f prime is never negative. And this is just kind of like the settings, the window settings I have. For 7, it says draw the graph of f double prime of x and find where the graph of f is concave up and concave down. So we have right here where the graph of our second derivative changes from positive to negative. Therefore, we're going to have a point of inflection here. So f is concave up when f double prime is positive. Therefore, and I just found the 0 here. So from negative infinity to the 16.094, or once you have your, you could find it graphically, or you could use the solve feature, and that second derivative you could just solve, set it equal to 0, solve for x. And then f is concave down when f double prime of x is negative, and that would be from that 16.094 to positive infinity. Now, I am going to use the graph number 7 to help us answer number 8. So it was asking for a point of inflection, and it does occur when f double prime of x is 0, and it also changes from positive to negative or negative to positive, so that's what we're seeing here. So everything over here is where f double prime of x is positive, and then right below it here, f double prime of x is negative. So we have a point of inflection occurring right here. But notice in the explanation that I'm piecing all of these together. So I make this mention here to tell me what I'm looking for. And then I say, well, f double prime of x is 0 when x is 16.094. f double prime of x changes from positive to negative at that x value, therefore f of x changes from concave up to concave down, and the point of inflection is at this ordered pair. Now all you have to do is take that 16.094, substitute that back into f of x, and then you'll get that 25, because it was asking to actually find the point of inflection. Alright, so hopefully you guys were okay with those. Next we're going to take a look at the review problems off of page 358. So looking at number 3, we are going to use some u substitution here. Alright, notice we have a definite integral from 0 to 1. So for number 3, I'm going to start by letting u equal 2x plus 1. Then du over dx is just going to equal 2, and dx is going to equal du over 2. So now my integral, and it depends on what you want to do. If you want to leave it from 0 to 1, that's fine. You have that choice. Or you could change the values. I'm actually going to change the values here. So when x equals 0, u is going to equal 2x plus 1, so u is going to equal 1. And when x is 1, u is going to equal 2 times 1 plus 1, so u is going to equal 3. So I'm going to go ahead and do that whole substitution here. So now I'm going to have the integral from 1 to 3 of 36 over u cubed times du over 2. So I'm going to take that 36 over 2, and that's going to turn into an 18 out in front, and then we'll have the integral from 1 to 3 of u to the negative third du. So then this becomes 18 times u to the negative second over negative 2 from u equals 1 to 3. So here I'm going to get 18, really negative 1 over 2u squared from u equals 1 to u equals 3. So I could take, since this is only one term here, I could really show that this is going to be a negative 9. I could factor that part out, and then we're going to get, let's see, that would leave us just with a, I'll just write it this way, 1 over u squared from 1 to 3. And then we could say it's negative 9. We'll get a 1/9 minus 1. 1/9 minus 9/9 will give us a negative 8/9. So we'll get negative 9 times negative 8/9. The negative 9's divide out, and we're just left with an 8. Alright, in number 4, we're going to let u equal 1 minus x squared. Then du over dx is going to equal a negative 2x, and then dx is going to equal du over negative 2x, which is good because there's a 2x in the problem that I want to get rid of. I'm also going to switch here, so when x is negative 1, u is going to equal, this becomes 1 minus negative 1 squared, so u is actually going to equal 0. And then when x is 1, u also equals 0. So what's nice about this, guys? The fact that these two u values are the same, we know what this answer is going to be. So I'm still going to show the substitution step. So this will become the integral from 0 to 0 of 2x sine u, and then du over negative 2x. It doesn't matter, because these are zeros, we can right now just go straight to that answer. That is just going to give us 0. So sometimes it's a benefit of writing this out, because if we didn't, we'd be going through a lot more work just to arrive at a 0. So all that work just to get nothing. All right, let's take a look at 6. All right, for this one, it actually becomes a lot easier. We don't need to do u substitution. So I want you to really maybe pause the video and then look closer at it. Is there something else we can do? Now, because this denominator is just a monomial x, what we can do is just divide this out. So if I took x squared plus 3x and individually divided them by x, I would get an x plus 3, and it's a lot easier to work with. So this becomes the integral from 1/2 to 4 of just x plus 3 dx, and we're just back to evaluating integrals as what we started with. So no need for u substitution here. We're just going to get x squared over 2 plus 3x. That is x equals 1/2, and then x equals 4. So putting a 4 in first, 4 squared is 16. 16 divided by 2 is going to give us an 8. Plus 3 times 4 is going to give us 12. And then minus 1/2 squared is 1/4. 1/4 divided by 2 is 1/8. And then plus 3 times a half, which is just give us 3/2. So we're going to get a 20 minus a 1/8 minus a 3/2. So we end up getting, I'm just going to turn everything into a common denominator of 8. So we're going to get 160 over 8 minus 1/8 minus 12/8. And this gives us 147 over 8. All right, looking at 7, we definitely want to do u substitution here. I'm going to let u equal the tangent x. And then du over dx is going to equal secant square x, which is nice because we want that secant square x to be gone. So du over secant square x is going to equal dx. So now this becomes, and again I want to try to write these out so that when x is 0, u is going to equal 0. And when x is pi over 4, tangent of pi over 4 is going to be 1. So we didn't get lucky with this one with having both zeros here, so we do have to do a little bit more work. So I'm going to write this as the integral as u goes from 0 to 1 of e to the u secant square x times du over secant square x. Secant square x is divide out. And then this becomes 0 to 1 e to the u du. And we know that the antiderivative of e to the u is just going to be e to the u. And then we're going from 0 to 1. So we get e to the first minus e to the 0, which is just e to the first minus 1 is our final answer here. All right, looking at number 8, we're going to let u equal the natural log of r. Again, because I want to get rid of that denominator r. So we're going to have du over dr is going to equal 1 over r. So r times du equals dr. Again, I'm going to change my values here. So when r is 1, natural log of 1 is going to be 0. And when r is e, the natural log of e is just going to be 1. So now this becomes, as u goes from 1 to 0, it's going to be the square root of u over r, and then times r du. So the r's divide out, and we have, sorry, that should be from 0 to 1. Of u to the 1/2 du. So now this becomes u to the 3/2 divided by 3/2. 0 to 1, so we're going to get 2/3 u to the 3/2 from 0 to 1. So this becomes 2/3 times 1 to the 3/2 minus 2/3 times 0 to the 3/2, which just equals 2/3. Hopefully everybody was doing okay with these two problems. Feel free to still email me at any time if you guys do have questions. Let's take a look at number 9. All right, for this one, I'm going to let u equal the denominator. So that du over dx is going to equal a negative cosine x. And that du over negative cosine x equals dx. This is an indefinite integral, which is good. We don't have to worry about changing any values here. So right now, this will become the integral of cosine x over u times du over negative cosine x. Cosine x is divide out, but careful. We're still going to have a negative sign here, so it becomes the opposite of the integral of 1 over u du. So this becomes the opposite of the natural log absolute value of u plus c, don't forget that. And then we could substitute back into u as the absolute value of 2 minus sine x, and then plus c. All right, looking at number 16. All right, so this says, let me write this a little clearer. dt, integral of dt over t radical t. What we could do is just look at this now as t to the 1 times t to the 1/2. So we're actually going to get t to the 3/2. So this becomes the integral of 1 over t to the 3/2 times dt, or the integral of t to the negative 3/2 dt. So we could just apply the power rule for integrals here. So this becomes t, if we add 1, we're going to get a negative 1/2. So t to the negative 1/2 divided by a negative 1/2 plus c. So this becomes, multiplying by the reciprocal, negative 2, we could say, over t to the 1/2 plus c, or just negative 2 over radical t plus c. So hopefully you found that one to be pretty okay. Again, knowing what we can simplify so we don't have to get involved with use substitution. So if we can, like a fraction, if we can divide something out, we could try that here. We just turned it into rational exponents, and we were able to use the law of exponents to add them together as we multiply the powers of t. All right, I think we just have one more. So here, looking at differential equations to solve, keep in mind, guys, you need to write out the steps that we're looking at here. So we could start, you could write this, instead of dy over dt, you could say y prime is 1 over t plus 4. So if you're going to just go straight to y, make sure you write it that y is equal to the integral of 1 over t plus 4 dt. So we need to show those steps as we're looking at it. So right now we could just say that y is going to equal, this is simple enough, you could still use substitution, but it's going to be the natural log of the absolute value of t plus 4. But because if we were to take this derivative of the inside stuff, we would just get a 1. There's no need to write anything else on the outside. And then we could say just plus c. And then using our initial condition of y of negative 3 is equal to 2, then we would have 2 is equal to the natural log, the absolute value of negative 3 plus 4 plus c. So we get the natural log of just 1 plus c. Natural log of 1 is just 0. So then c is equal to 2. And then our solution here is y equals the natural log of the absolute value of t plus 4 plus 2. So again, this is our specific solution. All right, so there is no new assignment that I'm giving you guys today. I just wanted you to look at these problems, go back and try them again. Tomorrow we will be moving on. I might start slope fields ahead of time, as I mentioned on with the AP exam. They will still cover that. So before I start Chapter 7 or give you any more review for Chapter 6, I might go ahead and start that. But please use today as a day to get caught up. Let me know if you have any questions.